Hello, Washington Liberty Chemistry students. This is your Unit 2 lesson on SI units, temperature scales, and scientific notation. We'll start first with talking about what SI units are. So, both a number and a unit must be included to express a quantity properly in measurement and chemistry. So in each one of these, identify the number and the unit in each quantity. So 1 dozen eggs, 2.54 centimeters, a box of pencils, and 88 meters per second. What is the number and the unit for each of these expressions? So for the first one, the number is 1 and the unit is dozen. For the second, the number is 2.54 and the unit is centimeter. For the third, the number is 1, and that's implied because of the quantity is only a box, and the unit is actually box of pencils. For D, the number is 88, and the unit is meters per second. And note that this one is in this case, the unit is actually a combination of two units. We call that a derived unit of meters and seconds. So what is the International System of Units? It's a system of measurement based on the metric system. And the acronym SI is commonly used to refer to this system and stands for this French term. Both the base and derived units in SI are defined. Now, what do I mean by a derived unit? A derived unit is a unit of measurement in the International System of Units that is derived from one or more of the 7 base units. So it's a relationship, like meters per second, for example. Now, in this slide, you will see the 7 base units of the International System of Units. They are here. For length, for example, it's meters. For mass, it's kilograms. And you can see the 7 base units. You can see some of the SI derived units, and they come from combinations of these base units. And they are for things like power or frequency or force. Those are all derived quantity units. The other thing you should be familiar with, since this is a metric-based system, is you should be familiar with the SI prefixes. And I think in previous math courses and science courses, you probably learned some ways to move between units. But in particular, you're going to want to circle and jot down kilo. We use that a lot. That's 10 to the third of a unit. Or centi, which is 1/100th, or 10 to the negative second of a unit, milli, 10 to the negative third. Those 3 in particular we use all the time. If you're doing any advanced chemistry or biology or physics, you're going to see things like micro and nano and pico. Okay, so now we're to part 2, temperature scales. Just a question. This is a really cool picture. Does anybody know what this is? What would you think it is? Well, the answer is it's something called a Bose-Einstein condensate. You're probably familiar with Einstein, this gentleman right here. Maybe not as familiar with Bose, but they proposed this. It is a Bose-Einstein condensate was, in theory, a 5th state of matter. That happens at very, very cold temperatures. And they proposed its existence. In 1995, they were actually able to have a Bose-Einstein condensate in the laboratory. So what is it? What you're seeing back there is a colorized lattice of tornado-like vortices within a spinning Bose-Einstein condensate of rubidium atoms. So you're really seeing atoms there. It's formed in an ultra-high vacuum at a temperature of only a few hundred billionths of a degree above absolute zero. Now, absolute zero is the coldest, and we're going to define this in a minute, but it is the coldest that anything can get. There's no temperature below absolute zero. So they're sometimes referred to as BECs, and BEC was recognized as a new state of matter in which the groups of atoms, rather than being sort of pushed together like solids where they were touching, they actually kind of merge into what they call a superatom. So the Kelvin scale has on it something called absolute zero. But you should know that the temperature scales used in science commonly are Kelvin, which does not have a degree, and Celsius, which is degrees Celsius. Temperature is a measure of the molecular motion of matter, and this molecular motion is called kinetic energy. So this is the idea. Let's just start with solid, because a superatom is hard to imagine. So solid, liquid, gas of, let's say, a particular compound. It's all the same thing. As the temperature increases, the motion of the particle increases. So in a solid, I think we wrote a definition saying that the particles in a solid sort of vibrate around a fixed point. So anything that has temperature at all, anything you can touch and it's not it's absolute zero, the particles within it are slightly vibrating, and that vibration is what causes temperature. Now, if we were to think of this as ice, this particular substance, the ice particles or the ice molecules would be vibrating very slowly. As you added energy to it, it would increase the temperature, it would increase the motion, causing a liquid, and then a gas would increase the temperature even more, and you'd have more motion. Now, this, notice, is the same substance, so you have to be careful about this. Any temperature, you have the same amount of kinetic energy, regardless of the phase. But if you're within the same phase, the gas will have more kinetic energy than the solid phase of the same substance. So here is a generalized graph of temperature versus average kinetic energy of the particles. And you can see it's a direct relationship, because as temperature goes up in Kelvin, so does the molecular motion, the kinetic energy. And you'll know this line is going right straight to the origin here of 0, 0. So that means that at zero temperature, at 0 Kelvin, you have no motion. And that is why, no kinetic energy. That is why that is the coldest you can get. So absolute zero. 0 Kelvin or negative 273 Celsius is called absolute zero. At that temperature, the kinetic energy of matter is also zero. And so therefore, you can see to convert between the two temperature scales, you just have to have the Celsius temperature and add 273 to it, and then you get the Kelvin temperature. So this is just a comparison. Now you can see here, here's our Fahrenheit scale that we only use for the weather here in the United States and is not used by scientists. But you can see that the Celsius scale, the freezing point of water between the Celsius scale is 0 degrees Celsius and 100 degrees for boiling of water. And what I want you to note here is that the 0 in Celsius is kind of arbitrary. Somebody decided, well, freezing point of water, that's a good spot. We're going to have that as 0. But you can see you can get a lot colder than that. We've all experienced probably sometime in our life when the temperature has gotten below 0 degrees Celsius. Now, the reason why 0 on the Fahrenheit scale, freezing of water is 32, and we have a 0 Fahrenheit is this is a very old scale. And at the time, 0 Fahrenheit, people thought that was the coldest you can get. But in fact, that's not the coldest you can get. You'll also note that the difference between 0 Celsius and 100 Celsius, which is freezing and boiling of water, is exactly 100. On the Fahrenheit scale, it's 180. So Fahrenheit degrees are actually smaller. That's why we really don't want to mess with them. Notice the Kelvin degrees are the same size. While the freezing point of water is 273 and the boiling point of water is 373, there are still 100 marks between the two, and that's why the conversion is so easy. So let's see if you get this. Convert from 0 degrees Celsius to Kelvin or vice versa. Take a minute and jot down your answers. So again, Kelvin is going to equal Celsius plus 273, and Celsius is going to equal Kelvin minus 273. See if you can do these in your head. Pause the video possibly and write down your answers. I'm going to go on to the key. So here's the key. So 20 degrees Celsius is just the Celsius plus 273. Minus 10 degrees Celsius is 263 Kelvin. Now 300 Kelvin, you have to subtract 273 from it. That's going to give you 27 degrees C. 100 degrees Celsius is 373, we're adding. And 150 Kelvin, we're going to have to subtract negative 273, and that's going to give us a very cold temperature of negative 123 degrees Celsius. All right, part 3 is scientific notation. And you're going to say, why do we need scientific notation? I don't like scientific notation. Well, in science, we use some very big, like the mass of the Earth, and some very small, like the universal gravitational constant numbers. And this is a lot more convenient. Let me give you an example. So in science, the reason why we use scientific notation, we deal with some very large numbers. For example, we're going to use a unit called 1 mole. And 1 mole is this number. That's a lot of zeros. It's actually 6.02 times 10 to the 23rd as a number. So we don't have to write that. We want to do this as an exponent. We call this number, by the way, standard notation when you write the whole thing out. Now in science we also deal with some very small numbers. So like this, look at this, is the mass of an electron. Now imagine if I wanted you to tell me how much a mole of electrons weighs. You'd have to do this multiplication, and that is just crazy, right? It's a lot easier if you're able to use scientific notation and follow the rules of exponents. So let's just define scientific notation again. Hopefully this is something you've done in math. It's a method of representing very large or very small numbers in the form m times 10 to the nth. So m is a number, and it's got to be between 1 and 10. So it's something like 1 or 9.999 can be m. But as soon as you cross over to 10, you move it over here. N is an integer indicating how many times 10 is multiplied. So for example, 10 to the second is 10 times 10, or 100. So let's just write this large number, which I have conveniently spread out for you, in scientific notation. Right now it's in standard notation. How do you do that? Okay, first you insert an understood decimal point, which is right here. Then you decide where the decimal must end so that the number is to its left. So and again, we want a number that is in between 1 and 10, and so it would have to end up here. Step 3, so we're going to do that. It's going to end up there. Then we're going to count how many places I need to bounce the decimal point until I get there. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have to do it 9 times, and that's going to be the exponent on the times 10. And then you rewrite it in the form m times 10 to the nth. And you should get this number, 2.5 times 10 to the 9th. So essentially, it's like 2.5 times 10, 9 times 10 times 10 times 10 times 10 will give you that number. The exponent is the number of places we moved the decimal. Now, it is also a positive number. We use positive exponents to indicate very large numbers, ones that are greater than 1. Now let's look at this one. This one is less than 1. So how do we do this one? Same basic steps. Sorry, we got this out of order. We decide, we see the decimal point. We decide where the decimal must end up so that one number is to the left. So we have to have a number that is less than 10 but greater than 1. And this is going to give us 5.79. We count how many places we bounce the decimal point. 1, 2, 3, 4, 5. 5, right there, okay? And then we have 5.79, which is less than 10, greater than 1. And then we rewrite it in the form m times 10 to the nth. I'm sorry, we have that decimal point right there. So you get 5.79 times 10 to the negative fifth. So why negative fifth? Because the number is less than 1. So we're essentially saying times 1/10, times 1/10, times 1/10, times 1/10, times 1/10. So the exponent is negative because the number we started with was less than 1. So this is a very small number. Okay. Now let's talk about if we have to do operations where we have to add, we have to multiply or divide exponents. So look at these two examples. So if we're going to multiply 10 to the third times 10 to the fourth, we just add these exponents because essentially this is just spreading out 10 times 10 times 10. That's 10 to the third times 10 times 10 times 10 times 10, 10 to the fourth. We've got 7 of them. We just add. So when you're multiplying, you just add the exponents. Here's another one. It's 5 plus 2, and this is the negative 3, so we're adding a negative 3. It's as if this was on the bottom, because that's what a negative exponent means. It's 1/10. So 5 plus 2 plus negative 3 would give you 10 to the fourth. So when you're multiplying, you add the exponents. When you divide, you subtract the exponents. So again, this is like canceling figures. If you have 10 to the fifth, and this line here, in case you're confused, means division. If you don't see a division sign, but you see a line, that's division. So 10 to the fifth over 10 to the third. So essentially in the numerator, we have 5 tens, and in the denominator, we have 3 tens, and we can cancel out 3 of them. and we're left with 10 to the second. But the shorthand here is you just do a subtraction. 5 minus 3, 10 to the second. Here's 7 and 12, so 7 minus 12 would be 10 to the negative 5th. 8 and negative 3, be careful because you're subtracting a negative, so it's 8 minus a negative 3 would be 10 to the 11th. And if you have the multiplication on top and on the bottom, you'll do what's inside the parentheses first, and then, so it's basically 10 to the 10th divided by 10 to the 5th. You can see it here, would be 10 to the 5th. Okay, now, this is great because we don't have that m number, but if we have that m number at the front, we're just going to treat that like a regular multiplication problem. So let's look at these. Why not try these? And essentially what you do is you follow the rules of exponents, because if it's multiplication, but then what you do is the numbers in the front, the m numbers in the front, you just do a regular multiplication. All right? So this is 2 times 10 to the 3rd times 4 times 10 to the 5th. So you'll multiply these two, and then to get the exponent, you're going to add these exponents. So see if you get the idea, all right? And then I'm going to show you the answer. So let's look at the answers. So this is 2 times 4, which is 8, and 3 plus 5, which is 8. So this is going to be 8 times 10 to the 8th. Now this one's just a little tricky, because 3 times 4 is 12. 3 plus 2 is 5. And so you can see you get 12 times 10 to the 5th. But that is not good exponential format, because this is greater than 10. So you're going to move the decimal. You're going to make it a smaller number. You're essentially going to bump the 10 over here. You're going to move the decimal over to give you 1.2. And if you make this smaller, you've bumped a 10 over here. You're adding here. 1.2 times 10 to the 6th. Expand it. You will see you get the same number. Now this is a division. I wanted to see if you could do this. This is a subtraction. So 5 minus 7 is the negative 2. But then you have to do 5 divided by 2. And I hope you can do that in your head, because 5 divided by 2 is 2.5. Now, I know that was a little fast, but given that all of you are supposed to have taken Algebra 2, I don't want to spend a lot of time on this, because you should know it, and hopefully with that review it refreshed your memory. However, you'll see in your notes that I have posted 2 videos. They're both about 10 minutes long, that goes over, first of all, just basic, taking standard notation and making it scientific notation, vice versa. So you can watch that one, and there's a link in your notes, or you can go to the slides and just click here, like this. Okay. And then this one is a multiplication, a division, what we did the last part in scientific notation. And again, lots of good examples that you can write down, because you are going to need to be able to do these things, and I want you to be able to do simple ones in your head. So that is your lesson.